Okay, this is what we have. 4.9.
You're not sharing your iPad anymore.
Okay, 4.9 and number 8. F prime prime x equals negative 4x cubed plus 4x squared plus 10x. F prime 0 equals 3. F0 equals 5. Okay. Find f prime x and f prime prime and fx. This is the classic antiderivative problem. You need to do the antiderivatives for twice. Now remember, whenever you do it for once, you have a constant which is plus c. You do it for twice, you have another plus d. You have two constants. The good news is you have two information to help you to figure out what the constants are. Okay, so this should be doable. Now, if you have f prime x here, prime x here, you just take the antiderivative to have f prime x, which is negative, okay, x to the fourth. Let me do this. 4 times x to the fourth times 1/4 in order to have x cubed, plus 4 times x to the cube times 1/3, plus 10 times x to the square times 1/2, plus a constant, which is negative this minus this minus 5x squared plus a c. That will be your f prime x. Now, of course, you want to know what c is. It's time for us to use this information. F prime 0, according to what you have here, plug in 0, we find you only have c, and that thing should equal to 3. So finally, f prime x should be just this one plus 3. Okay, so the first one done, and this information has been used. Now the second part, fx. Now let's take the antiderivative of this, which is negative 1/5 x to the 5, 1/4 x to the 4, okay. Now simplify a little bit. Plus a d, and you know f0, if you plug in, according to what you have here, you should receive 5. Then you know the final answer should be this. I'll just type this one in. Weber should take it. Aaron?
4.8 and 4.9 are just antiderivative, right?
4.9 is antiderivative. 4.8 is Newton's method.
Okay.
Yeah. Other questions from homework? All right. Let's continue. 5.1, we were trying to find the area under a curve. So this is where I need to share my screen. We did this, so we just briefly go over it to remind you. Okay. We were talking about how to find the area under a curve. Okay, something like this. We'll assume the area is actually under the curve is positive. And what we do is basically we cut the intervals into several pieces, equal pieces, okay, rectangles. We calculate the rectangles and we sample a point from the rectangle. In this case, we use the right end point. And from here, you can see we overcount here, we overcount here, we undercount here. We do partially overcounting and partially undercounting on this rectangle. It's not accurate. How do you make it more accurate? You take more rectangles. Okay, you still overcount, you still undercount, but from here you can see it's more accurate simply because the part that you're missing is fewer. More and more, and you just do 200. And suddenly everything becomes super accurate. Hopefully you're happy, and if you're not, just do more. Okay? From here you can see this is actually how the computer calculates the area under a curve. They just take a lot of rectangles. Of course, as a human, we don't care about how you do the approximation. It can be done by computers, but when will you have the exact answer? You take n goes to infinity. You take infinitely many rectangles. And hopefully that limit exists, and we know how to take the limit, right? That will be our final answer. Is the idea clear? That's what we have for Riemann sum. Okay, now I just stop sharing this and reshare this. That's what we are focusing on. Now let's try to formulate the idea and put them on paper. Screen share. All right. I was trying to find the area under this curve from A to B. Okay, let's repeat what we had last time. You have an interval. The first thing you want to do is you want to divide it into small subintervals. N small subintervals. Okay, so A, B, cut. You give them names. This is the first interval, this is the second interval, this is the third interval. And you have all the points to be A equals x0, and then you have x1, you have x2, you have x3, all the way to xn minus 1. And finally, the last one is B equals xn. So x1, x2, x3, you have all these intervals. Xn minus 1, and finally the last one is xn. In this way, you have n plus 1 points corresponding to n intervals. Well, over the ith interval is going to be xi minus 1 and xi. For example, the second interval is x1, x2. The third interval is x2, x3, and so on. So this is just a notation. The width of each interval, if you take equal width, is going to be the total length divided by n. We need this because this will be the width of the rectangle eventually. We need it to calculate the area. So that's the first step. Everything up to here is done. Second, now we have each piece. Each piece may look like this. We say we don't want it. We want it to be a rectangle. Okay. So how do we do that? Number one, we have a width, and width has no problem. Number two, to find the area, we need a height. Good so far? Now to find the height, you just need something roughly the height of this, right? So what we do is, instead of taking it randomly, what we do is we pick a point on the function and just say, hey, I'm just going to take this rectangle. And this point here is going to be what I call xi star. That will be my sample point. The sample point on the interval good so far? You can pick the sample point for whatever you want, but if you want some easier computation, there is certainly a quick way to pick it. You can pick it to be left point. That tells you xi star is going to be where your interval starts. You can pick the right point. You can also pick the midpoint. These are just some popular ways of picking it. It really doesn't matter which one you pick. You can even pick the part at 1/3, or you just totally sample them randomly, as long as you just make sure they're in the interval. All right. After that, we have each rectangle. We sum them together. We give it a name. We call it the Riemann sum. R, and that depends on how many rectangles you take, which is nothing but the sum of all the rectangles with the width times the height. And finally, the exact area is going to be limit n goes to infinity, Rn. You can take 1 million rectangles. It's not going to be exact. It's going to be an approximation. It's going to be a really nice approximation, though. Okay. But to have the thing accurate, you have to take the n to be infinity. Okay. If you type this one in Wolfram, say find the area under the curve from where to where, this is how Wolfram calculated. Okay. The only difference is Wolfram doesn't do it to the infinity. Wolfram probably do it up to 1,000 or something like that to give you something really, really close, but it's not going to be the right answer. That's why all the answer you get from Wolfram is usually decimals. Okay, they don't give you something like 1/3, 4/3, unless it's very simple, because they're trying to do approximation there. Conceptually, is the idea clear here? Nice. Let's try some examples. It's going to be easy. It's going to be long. Okay, be patient. You definitely got every single step. Just try to make sure that all the steps make sense in your mind. Okay, but let's say approximate. Y equals x squared on 1, 2. Using 4 rectangles. And the right point former. Basically, you cut the whole interval into 4 parts. For each part, you do a rectangle. And moreover, for the height of the rectangle, you do the right end former. That's what we're looking for. Okay, from here you can see it's an overestimate because it's bigger than what it should be. All right. Step 1, take the interval 1, 2. Cut it into 4 parts. What you have here is 5/4, 3/2, and 7/4. You count it, you have 1, 2, 3, 4, you have 4 intervals, equal length. The width is going to be 2 minus 1 divided by 4, which is 1/4 each. Second, for each rectangle, the first one is going to be this, 1/4. Now remember, we're taking the right end former. So for the first interval, you should really take this number. That's what we call right end former or right point former. So If that is okay, you know f. F is x squared. So to make your computation a little bit easier, because you're going to sum them together, you better make them all to be base 64. So final answer R4 which is 61, 110, 174. Which is roughly 2.7, 27188. Sounds good. This is the overestimate. Okay, the real one is going to be smaller than this. Okay, but nonetheless, this is the first start. Do you want to get it better? Do 20 rectangles. Do 200 rectangles. Of course, you don't want to do it by hand. You use a computer to code it. Okay, but it's a piece of cake for them to actually finish within no time. Sounds good? Try one by yourself. Okay, approximate y equals sine x on 0 pi. Using 3 rectangles. Actually, let's use 6 rectangles. 3 rectangles. Doesn't matter. And the left point formula. It's pretty amazing, by the way. You know sine curve for a long time, right? Have you ever wondered how big this is? You know circle. Is this one bigger or less than a circle? Half circle. Well, later we will be able to figure out. For now, 3 rectangles. Da, da, pi, pi over 3, 2 pi over 3, left formula, left formula, left formula. So the first rectangle is actually has a height 0. Okay, let's do it quickly. By the way, it started snowing. All right. Looks good. That's how we do the Riemann sum. Okay. In the exam, I will give you something similar. And during the homework, you will have something similar. Okay. I would say usually it's no more than 6 rectangles. If it's 6 or 4, which is big number, it's going to be super easy to compute. Okay. Easy numbers. And then it will be either left point or right point, and very unlikely but possible, midpoint. Okay. Very unlikely, but possible. I believe the idea is clear. Okay, if you need more exercises, go to the web work. You will be able to figure this out. It's very easy. You just need to get familiar with it. All right. I think now if I ask you to do 20 rectangles for any random function, given a calculator, you will be able to do it. It's not too hard. Of course, in mathematics, what we care about is we want to know what the limit is. We want to know the exact number. Okay, so let's try to push it to the limit. And see how hard or how easy to do it. Okay. Well, let's do the easy examples. Make sure that we put our foot on the ground. Try something that we already know. Let's try y equals x on 0, 1. Do you know that area? It's a triangle. So it's 1/2 times 1 times 1, which is 1/2. Of course, we don't want to take the shortcut. We want to say, hey, we want something works for any function. So let's go with the Riemann sum and see how hard or how easy to get this number, 1/2. Okay. Okay. With that in mind, this time we cannot take the shortcut. We cannot say 4 rectangles. We have to say n rectangles. Okay. Try your best to write down all the stuff you can. 0 to 1, you have n rectangles. How long is each rectangle? Which is just 1 over n. The total length is 1. You have n rectangles. Each one is 1 over n. That means start from the first one. x0 is 0. Okay. What's this point? That's 1 over n. This is going to be 1 over n from 0. Okay. What about this one? That's 1 over n from 1 over n. That's 2 over n. Good so far. 3 over n. Dot, dot, dot. N minus 1 over n. Finally, n over n, which is 1. So you have n intervals. Each one has a length of 1 over n. So far, so good. Second, I want to use the right-hand former. You can use left or middle point or any, but like we said, when you take the limit, it really doesn't matter which one. Let's take the right one. Okay. Then this is the ith interval, xi minus 1, xi. Moreover, you can write it out. It's I minus 1 over n and I over n for the ith interval. Okay. And you want to take the right end former. So this is going to be f, the right end. Still okay? But your fx equals x. So this is just I over n due to fx equals x for this particular one. Still okay? All right. So this rectangle is going to be the width times the height. Okay. Now what you want to do is you want to take the Riemann sum, which is sum from 1 to n, 1 over n times I over n, which is sum I from 1 to n, I over n squared, which is 1 over n squared plus 2 over n squared plus 3 over n squared plus n over n squared. That's what you're trying to do. Make sense so far? All right. You could do this for 4 rectangles, but you did it for n. So now if I ask you what is R4 if you use 4 rectangles, it's going to be 1 over 16 plus 2 over 16 plus 3 over 16 plus 4 over 16 if I use 4 rectangles. Okay, what's the answer? The answer is going to be 10 over 16, which is pretty close to 1/2. What if I want 8 rectangles? It's going to be 1 over 64 plus 2 over 64, dot, 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 plus 8 over 64. It's going to be another number. It's going to be even close to 1/2. Still okay? So pick different n, you have different ones. But of course, what do we want? We want the last one. We want the last one when n goes to infinity. N is not 1 million, and n is not 1 trillion, n is infinity. Okay, that's our idea here. All right. Good, good. Number 4, what's the limit? That means you somehow need a better formula for this. Why? Because you have too many terms. I don't mind if as n increase your number change, but I really don't want as n increase the number of points change. Okay, so let's just say this. Do you have a way to write all these terms into one term? Okay, that's the key here. Sounds good? All right, what's this? It's n squared, 1 plus 2 plus 3 plus 4. It's the sum of the first n natural numbers. Do you recall you have learned something like this before? It's a formula. Have you seen it before? If no, let's do it from fresh. Basically, just take some easy examples. How do you do 1 plus 2 plus 3 plus 4 plus 5 all the way plus 10? How do you do that? Of course, not actually doing it. Okay, do it quickly in a clever way. We want to do n. Have you seen something like this? You just rewrite everything backwards? Okay, plus 1. What's the advantage of that? Well, what's this? 11. What's this? 11. What's this? 11. Can you see they're all 11? Can you see why? Well, going from here to here, from 1 to 2, you basically change this. You increase this one by 1, right? Now at the bottom, from 10 to 9, what do? You reduce this one by 1, right? You increase by 1, you reduce by 1, and then you sum them together. The sum doesn't change. The sum is still the same. Good so far? Okay, so every single pair here is 11. How many pairs do you have from 1 to 10? You have 10 pairs. Good so far? But how many times have you summed all the numbers together? You did it for twice. Forward ones, backwards ones. Okay, so together 1 plus 2 plus 3 all the way to 10 is going to be 110 divided by 2, which is 55. Sounds good? Similar ideas. If you want to sum everything from 1 to 100, how do you do it quickly? Plus 98 plus 99 plus 100. Well, do the same thing. Number 1, I'm going to do it for twice. 100 plus 99. 1 forward, 1 backwards. I just keep in mind, like when I finish, I just need to divide by 2. Done, right? Second, if you want to do it for twice, you do this. What is each one? Well, 1 times how many times? Times 100 times. So this is going to be 50, 50. That's what number you're going to get if you sum everything from 1 all the way to 100. Sounds good? All right. Let's forget about 10. Let's forget about 100. Let's take any n. What do? You write them backwards. Good so far? When you finish summing them together, you divide by 2. All right. That's it. This, what are they? N plus 1 for every single pair. How many pairs? From 1 to n. N pairs. Sounds good? Okay, through this way, the top can be rewritten into this formula through whatever argument we just did. Sounds good? Another way to think about it, there are many different ways of doing it, just to show you a little bit, because this is pretty fun by summing a lot of numbers together. When I was a kid, I used to eat those kind of chocolates, which I don't know why, but they divide them into grades. Make sense here? Okay. And trust me, this actually is what I figured out by myself when I was a kid, which I found pretty amazing. If you eat those kind of chocolates every day for half a year or something like that, eventually you just play with it. You see, well, I need to find a quick way to count all the grades, right? I always like when I eat, I just eat 1 grade, 2 grade, 3 grade. Eventually, I developed my way of doing 1 and then 2 and then 3 and 4 and 5. As I grow bigger, my mouths become bigger. But then eventually you figure out, like, how do you sum all these numbers together if you just increase by 1 every single time? Do you realize this is exactly the same thing as what we did? Natural number, you sum them together. This is what I figured out. You don't like this. You like squares, right? You like rectangles because you just take the size times the, the height, done. Soon enough, I learned that if I take the same chocolate, I just flip it and put them together. What do you get? You got 2 copies of it. Okay, so how about you do them together, but then you just divide by 2 when you finish. That's fine. But once you put it here, what happens? The whole thing becomes a rectangle, right? How many are here? I did 5, but you can easily see this is going to be n if you stop at n, right? That tells you this is n, right? But what about this? By putting another red one here, that's going to be n plus 1 because it's a little bit taller when you stack them together. Meanwhile, you still have n on the other side, but meanwhile, you count it for twice, so divide by 2. Okay, so that's another way to count this. There are many other ways, which are pretty clever, okay? But I think for now, we all buy into this idea that probably this is a formula. Sounds good? That's your Rn. What's your job? Your job is try to find when n goes to infinity, what happens to this? Which is when n goes to infinity, what happens to this? Which is what happens to n equals infinity for this with the formula we just did. If you want, you can put the 2 down to just make everything looks a little bit cleaner. What's the limit? What's the top? Infinity. What's the bottom? Infinity. How do you handle infinity over infinity? Number 1, L'Hopital. Certainly will do. Okay, number 2. Actually, we used something earlier. Leading terms. Right? What's the leading term on the top? What's the leading term on the top? N squared. What's the leading term on the bottom? 2n squared. Okay, what's the limit? 1/2. It matched. It matched what we computed by triangles, right? This one worked. So that's the final answer. Sounds good? It's pretty amazing. Think about what you just did. You take the sum, you put it in there, and you say, I was trying to find the limit when n goes to infinity for this. Good so far? What's this term when n goes to infinity? 0. What's the term? This term when goes to infinity? 0. Do you realize every single term is 0 when n goes to infinity? How many are there going from the first one to the end? Infinitely many ones. Still okay? You put 100 zeros together, it's still a 0. You put 1,000 zeros together, you took 1 trillion zeros together, it's still 0. But if you put infinitely many zeros together, you may get something. In this case, you got 1/2. It's pretty amazing if you think about it. And then again, we verified 0 for infinity times may give you something. It may not just be 0. It may not just be infinity. It may be something in between. So this is why it's indeterminate. This is what we just did. It worked. Do you like it? The idea is so simple. The computation is so messy, right? Okay. Number one, this is a freaking easy function. I don't even want to imagine what would happen if I put x squared here. Let's imagine what's going to happen. Number one, this stay unchanged. This has nothing to do with the function. So step one, as easy or as hard as before. Doable. Step two, just plug in all the numbers, as easy as hard before. Can you see what will change? If you change the function, this will change. Right? If that change, everything here changes. And if that thing just changed a little bit, for example, it changed from this to this. Do you know how to sum a lot of squares together? If we change it to be cube, do you know how to do that? If I change this to be sine 1 plus sine 2 plus sine 3, depending on the function, do you know how to do that? Not really. Can you see that? The original difficulty lies in here. That is from this step to this step. In general, it's really difficult for you to write that thing into one formula and then take the limit. So this is the most difficult one. Everything before, easy. If you can do this and find this one, everything after that will be easy because we know how to take the limit. It's just how to write that formula, how to write that chocolate. And for general cases, you don't have chocolate. You need to create some other ways to do it. That's the most difficult part. How difficult? Almost impossible. To be frank, even for the big mathematicians, they can only handle so much. Okay, a general function, they can't do it. Good so far? So this is just for you to do it for fun. Okay, but now we have some calculations. Number one, it's working. Great. Number two, it's super difficult. For hand computing. In general, it's almost impossible. That means we won't use this one for hand computing later. Sounds good? We need something else. Second, however, it's great for computers. Why? Because computers don't care about the limit. They just say, well, please do it for 1,000 squares. They just say, okay, I'm going to do it for 1,000 rectangles. Sounds good? And for application point of view, actually 1,000 rectangle for normal functions are pretty good. Okay? You did everything here. You receive an answer, which is pi over 3. Why don't you just let the computer do the decimal? Maybe it's even better than pi over 3 because you don't even know what pi over 3 is. You still have to take the approximation, which you use 3.14 divided by 3. But remember, pi is not 3.14. Pi is 3.14 with many other decimals. Okay? So actually, in real life, using computer is good enough. So Riemann sum is still very useful, just not for human. Sounds good? Okay, we will not do any more examples. You will see something in your web work. In the exams or anything, I will never ask you to actually do this to the end, unless I give you some help during the way. For example, I can tell you, if you go all the way up to here, I will tell you the next term is this. You don't have to actually figure that thing out by yourself. Okay, so all you need to do is actually understand this process, how this works. Okay. All right. Number 3. Let's talk a little bit about Riemann sum. By the way, does anybody know this guy, Riemann? Okay. If you don't, try to Google him. He's a really great mathematician. You guys know about Einstein, right? What Einstein did with his general relativity is based on Riemann's work on Riemann geometry. Okay, so he's actually a really big mathematician. Everything you heard about high-dimensional space, like 4-dimensional space, he started everything there. Okay, he actually started the whole thing. If you read sci-fi from the end of the 19th century, okay, there is a boom in the sci-fi about time traveling, about high-dimensional things, about flat world. It's all inspired by his work. But for now, he's famous for one hypothesis, which is called Riemann hypothesis. Okay, you can Google it. It's one of the 7 millennial problems, which has a bounty on it, which is $1 million. If you could solve the Riemann hypothesis, you will receive $1 million. Okay, so Google it. It's pretty fun. And 2 years ago or 1 year ago, I don't quite remember. As you grow older, time doesn't mean that much to you. Okay, and there was one guy whose name was Adler. He was pretty old and claimed that he proved Riemann hypothesis. But 1 year or 2 years has passed. I haven't received any new update on that. Probably his proof is wrong, or nobody actually even care to read his proof. But yeah, that's what's happening with the Riemann hypothesis. Okay. It all narrowed down to one question. Can you always find the area? If you do this process for any function you find, is there a guarantee that you will always be able to finish it and find a number? What can go wrong? You're taking a limit, right? Is there a guarantee that a limit always exists? Not really, because you have written DNE for a long time. You know, for a lot of limits, it simply just does not exist. Okay? So it narrowed down to this question. When can we use Riemann sum? Sometimes it's not usable. And Riemann gave us a very simple conclusion, which involves the upper Riemann sum and the lower Riemann sum okay, both of them share a similar formula. We call it Rn with a bar to say it's upper, with an underline to say it's a lower, which is sum. So far, the same. The width. The only difference lies in here. You take a bar and you take an underline. Here, the bar means the maximum on the interval. This one means the minimum on the interval. Let me explain what I mean by that. Remember we have something like that? We said we can do left point formula. That's one way. Okay, we say we can do right end formula. We can do the midpoint formula. We have all these kind of ways. Good so far? And we say which way you pick it really doesn't matter. Well, this is something very tricky. You're working on thin ice here. Sometimes it matters which one you pick. Which it's going to be a very rare case, but it will happen. So what Riemann did is, he just said, well, why don't we just always pick the maximum on each interval? Doesn't matter it's the left point, right point, or some point right in the middle. Okay, let's just pick the maximum. Okay, then we do it again, but this time we only pick the minimum. Upper, lower. Good so far? Then any other Riemann sum will be in between. It's going to be smaller than the maximum if you do it always maximum. It's going to be bigger if you do it always minimum. Good so far? Okay, so let's write it down. Any other way of picking points will be between these two ways of picking points. Agree? Okay. So how do you make sure that this one has a limit and the limit exists? Looks familiar? How do you make sure that? You take the limit on the left. You take the limit on the right. How do you make sure that the one in the middle has a limit? You can only make sure the left and the right equals each other. Or you can make sure that the Riemann upper sum equals the Riemann lower sum. Make sense here? How do we call this? The squeeze theorem. Okay. So when can you find the area? When will the limit exist? When upper sum equals the lower sum. When can you say that which sample point really doesn't matter? Okay, when the upper sum equals the lower sum. Because even if you take the maximum and the minimum, that's the biggest gap you can difference you can have. Even that goes to 0. Good. Then really, if you pick something other than the maximum or minimum, of course it doesn't matter. This is the worst case, and they still match. Right? Okay. That's how we check if some Riemann sum can be done or not. It's not going to be easy, but this is how we check it. Okay. With that in mind, I can give you an example for you to think about. Can you do Riemann sum for this function? Actually, we will do it next time. I will just write it down. You think about it. This is the same function we had before. It's 0 if it's irrational. It's 1 if it's rational. Okay. Can you find the area of fx on 0, 1 using Riemann sum? Okay. Try to think about it. Try to go from the upper and lower sum approach. See if they're equal. If they're not equal, then what number you get really depends on how you pick the sample point, which means it's not doable. All right, that's all for today.